Yeah. Okay, so strong induction. Didn't feel good. So we talked about this idea that sometimes you're doing an induction proof, you can't just use the previous case. You need like an earlier case, but not necessarily the previous case. And so the idea was that for the inductive case, or the inductive step, I should say, don't just assume P of k is true, but assume that sort of like, maybe I'll just do it this way, P of n naught, P of n naught plus 1, P of n naught plus 2, all the way to P of k minus 1 and P of k. And the n naught is like the base case, right? Base case. Okay, so assume these are all true. And then prove P of k plus 1. So you're basically assuming everything from the base case up to your current position, right? Because that should sort of make sense. It's like the ladder metaphor. It's like if we started at the bottom rung and we're somewhere higher up the ladder, then that must have meant we were able to make it to all the previous rungs. Yeah.
So why do we have weak induction then? If strong induction already covers for the
That's a good question. So it turns out like weak induction, strong induction, and we're going to talk about the well-ordering principle are all equivalent statements. And I guess there is a thing where mathematicians like to use the least hypotheses they can to prove something. So you're like assuming, I mean, in some sense, it's funny because the words strong and weak, I used to have trouble remembering which is which because you're making the hypothesis stronger, but in some sense that's making what you're doing weaker because you need more to be true before you can move on, before you can prove something. And so, yeah, it's sort of like an interesting question of like, strong means making the hypothesis stronger, like what you're assuming stronger, but that's a higher bar to clear. And it's sort of nicer if you can just, say like, let's just use the previous case. I mean, I don't know if that's that satisfying an answer to your question, but it does turn out like, I don't know if I'll fully prove it, but like, yeah, weak induction, strong induction, well-ordering principle are all equivalent to each other. So, and I actually really like the well-ordering principle. We're going to do some well-ordering principle proofs today. Okay, so the example I was just going to say was like, so last time I think at the very end of class, I did every integer greater than 1 has a prime divisor. I'm going to change that slightly because I think this is even a more compelling proof that every integer greater than 1 has a prime factorization. Okay. So it's interesting because I'm not saying it has a unique prime factorization. That's actually a significantly harder thing to prove, that the factorization is unique. And we actually need sort of all of axiomatic number theory to build up to that. And I can tell you number systems where prime factorization is not unique. There's some interesting, if you take number theory, Math 2502, number theory and cryptography, you'll definitely see examples of that. But actually just saying that you can sort of break every integer down by multiplication until you can't break them down any smaller seems like something that's kind of a universal thing. Like you could always break stuff down. So the proof is by, I guess I'll say strong induction. I guess I should call this N by strong induction on N. And we had the base case, like, we could do a couple base cases if we wanted. Base case is, we could say 2 is 2. There's a prime factorization of 2. 3 is 3. 4 is 2 times 2. However many base cases you need to build up a few. You don't have, you can just use the first 2 as your base case. But and then the inductive step now. So inductive step. So it's assume every integer between 1 and k has a prime factorization. Actually, between 1 and, maybe I should say between 2 and k inclusive, or I'll just say it, every integer m satisfying 1 less than m less than or equal to k has a prime factorization, right? Basically can be factored into primes. Okay, if we assume that, and then we want to prove k plus 1 as a prime factorization, right? We want to show k plus 1 as a prime factorization. Okay, and then there's kind of like 2 cases. Either k plus 1 is prime or it's not, right? If k plus 1 is prime, we're done, because k plus 1 equals k plus 1. Right, kind of like I wrote 2 equals 2 down there. If k plus 1 is not prime, then it's composite, and so it factors into 2 smaller numbers, right? There exists a and b in the natural numbers, and actually we should say that a and b are between 1 and m plus and k, right? It's going to factor into 2 things smaller, but bigger than 1, such that k plus 1 equals a times b. All right. It's kind of what it means to be composite. You can factor into 2 smaller pieces, neither of which is 1 or itself. Okay, do you see now where the proof's going? What can I say about A and B? Yeah. They both have prime factorizations, right? Yeah. By the inductive assumption, A and B both have prime factorizations. Assumption A equals P1, P2 through P. I need indices that I haven't used. I used M, N, K, L. And B is maybe Q1, Q2 through QR, where the PIs are prime and the QIs are prime. QJs are prime. Makes sense? So you can factor both of those. And then is it clear now that k plus 1 has a prime factorization? Why? Don't mean this to be a hard question, just kind of the obvious, right? You stick them together, right? You just stick them together. And then k plus 1 is P1, P2 through PL times Q1, Q2 through QR, which is a prime factorization. Okay, so I kind of like this proof because you kind of break it down and then you can, just write the prime factorizations of the two smaller ones and then put them together. And that's it. So that proves the inductive step. So therefore, by induction, every n greater than 1, every n greater than 1 has a prime factorization. I always feel the need to write the final statement. And again, I'll say I sometimes don't always write the capital P of whatever, especially since I was using P's, little P's anyways in here. Make sense? Okay. Yeah, so it's funny because I looked in a bunch of books and most of the strong induction examples are this or the other one I gave. So I mean, I think there are other places strong induction comes up, but you sort of need more context, more mathematical context. But this is something we can prove fairly easily. I mean, a lot of times you are just trying to piggyback from one step to the next, and so you can just get away with weak induction. But you're right, you can assume the strong induction hypotheses. Okay, I also wanted to talk about the well-ordering principle, which is something very similar, although it looks weird at first. So this is that last axiom on the axiom for the integers. And I claim that it actually, maybe I should pull up that sheet. I claim that we've had the ring axioms, all the basics of the operations, right? And then we had this ordering axiom about what it means to be positive. And then just go ahead and, I did post the problem set 3 solutions in text source if you want to look at it. Sorry, let me share this screen real fast. But yeah, if you look at this axioms page, right, we had all these sort of axioms 0 through 6, which are the basic ones. We had this axiom 7, which we talked about for a while to get the ordering, right? And now there's this axiom 8. And it turns out, I mean, this is something that you maybe would prove in an abstract algebra class, like the ring theory class, that this actually uniquely determines the integers. There's any set that satisfies these axioms basically has to be the integers. There's a way to make that precise. There's something called isomorphism of rings. So I mentioned a ring is anything that satisfies those first 0 through 6 axioms. You could prove that any ring that satisfies all those axioms is isomorphic to the integers, basically means structurally equivalent to the integers. But, and so it's kind of weird, but this is kind of a strange axiom, right? So let me just, let me just write it down. So every non-empty subset of the natural numbers, subset of n, has a least element. Has a smallest element. I say least there, I don't know, smallest. For some reason, mathematicians usually say least, but then that sounds weird. Smallest element. Okay, so by the way, what does that mean? It's like, I could even say that a little more mathematically, right? I.e., given a subset of the natural numbers, S subset of n, S not empty, not equal to the empty set, there exists an A in S. I guess you actually had to do something on the homework about shows like how you'd state 17 is the largest prime number or something like that. Or, so you can probably, so such that for all B in S, A is less than or equal to B. Does that work mathematically? Yeah, there's a special element called A that's less than or equal to. Obviously it's less than or equal to because B could be A itself, right? Does this feel true, by the way, for subsets of natural numbers? If I take all the odds for the smallest one. If I take all the primes ending in 73. The last two digits are 7 and 3. Well, 73 is prime, but if I take all the primes ending in 60, well, it's actually still true because that's an empty set. Prime can end in 0. Yeah, by the way, this is not, I should say, by the way, not true for example, like the positive rationals. This is, again, one way we distinguish the integers from the rationals, right? Like, say S is all X in Q such that X is greater than 2. Does it have a smallest element? Is there a smallest fraction bigger than 2? No, it's 2.000001. That's the smallest one, right? Okay. There are actually people called constructivist mathematicians who sort of don't really believe in infinity or an infinite number of things, or like they're sort of like at a maximum. It's like a maximum number you could build in the time of the universe, like in the whole age of the universe is like a maximum number you could build. So like, there's no reason to ever consider anything larger than that. And you could, in the whole age of the universe, you can only get so close to 2 without equaling 2. You just kept making smaller and smaller. But okay, we're not going to talk about them. They're weird. Even for mathematicians, they're weird. Yeah, this is not true. There's no smallest element of this. But we do think of the integers as having this nice sort of property of being sort of discretely separated, like there's kind of, all this. And I think in the outline for today, I mentioned this, that like, it's actually a way to say that there's a next integer, right? We can use this to say there is a next integer. So for example, what I mean is like, given, n equals 243, consider S to be the set of natural numbers, say A, and natural numbers such that A is greater than 243, right? First off, we'd have to say this is not empty. Why is it not empty? It's kind of a weird question. What can you say is in this set? These aren't really meant to be trick questions. It's kind of like, what things would you say are in this set? Yeah, 243 plus 1, like that's certainly a construction we can make axiomatically. That's in the set. Now it sort of turns out that that is the least element, right? Or you could show that 243 plus 243 is in the set. natural numbers. Yeah, like the way addition works, you could show that was greater than 243. So S is not empty, so it has a least element. G thus has the smallest element. And that's your next integer. Now, it's kind of, I don't think it's actually obvious that the next integer is 243 plus 1. Right? How do we know that there's not something in between 243 and 243 plus 1? You know, this just says that there is a smallest element of that set, but it doesn't say that that smallest element is 243 plus 1. It's kind of strange to think about. We have so much experience with the integers that it's like hard to take a step back and think about it this way. But right, so I guess the question is why? We know it's 243 plus 1, but why? 243 plus 1, but why? So actually, there's a proposition I want to prove using the well-ordering principle. Okay, sorry.
How do we know that S is not? How can we just state that?
Well, you can say that 243 plus 1 is in the set because you can prove that 243 plus 1 is bigger than 243. Okay. Because we proved 1 is greater than 0, for example. Yeah. And if you add 243 to both sides. So I think it's possible to show. Yeah, I didn't really say it, but it's a good, it's a good thing to kind of pin down. So here's a proposition that's going to seem really super duper obvious. But there's nothing in the axioms that tells us this. There are no integers between 0 and 1. I mean, it seems like a really silly thing. We know that's true. We like know it so deeply in our bones that this is true, right? But if you say there are no integers between the additive identity and the multiplicative identity, that makes it alien enough that it may become less obvious. You know what I mean? Like, there's some, like, why not? Why is there no integer between the additive identity and multiplicative identity? There are rational numbers between the additive identity and multiplicative identity. So again, somehow that should be somewhere that if we're going to justify this, it's probably going to come down to the well-ordering principle, because the well-ordering principle is the only thing that's kind of different between the rationals and the integers. We also have proved that 1 is greater than 0. So we can actually even say between 0 and 1 means greater than 0 and less than 1. So there does not exist an x in Z such that 0 is less than x is less than 1. Or you could say for all x in the natural numbers, like there's different ways to say this. For all x in the natural numbers, x is greater than or equal to 1. Right, we're kind of saying 1's the smallest natural number. Because we know everything that's greater than 0 is a natural number. We proved that. Okay, so I want to prove this, and I want to use, I'd say this is something that would be quite hard to prove by induction, actually. One thing I thought about doing, and I just sort of skipped over, was I could rewrite this proof in terms of the well-ordering principle. It might be a nice aside, maybe not to write anything down, but just to say it. I could let S be the set of all integers that do not have a prime factorization. That's one way to construct a well-ordering principle proof. Is like, what if S is the set of integers greater than 1 that don't have a prime factorization? And our assumption, and we assume it's not empty, and we want to contradict that. Well, if it's not empty, it has a smallest element. And its smallest element is something like this k plus 1 here. And so it can't be prime because then it would have a prime factorization. So it must factor into two smaller numbers. But those numbers are outside the set because they're less than the smallest element of the set. Therefore, they have prime factorizations. And then you can just kind of repeat this proof. It's a little bit strange way to think. I mean, I think this is kind of a little more natural, but so in fact, you've shown that the smallest element actually does have a prime factorization, which is a contradiction, because it was not supposed to. And then that's your contradiction. So it actually was an empty set. Anyways, that was kind of a lot, but you can sort of imagine reformulating this proof in terms of the. That's what you do is you just consider the set of things that don't satisfy the thing you're trying to show, and then pick the smallest element and then show a contradiction. Yeah, okay. But for no integers between 0 and 1, I would have a hard time. I feel like I would have a hard time reformulating that as an induction proof. But the well-ordering principle proof is very nice. I mean, it should be able to be reformulated as an induction proof. Somehow I never really thought about how to do that. So proof. Well, we suppose there are integers between 0 and 1, right? Suppose there are integers x such that 0 less than x is less than 1. So let's consider the set of all of them. Consider S to be the set of x in Z such that 0 is less than x is less than 1. Okay. By our assumption, S is not empty. And we want to get a contradiction. We want a contradiction. Right, we're doing a contradiction proof. So, I mean, I can sort of start to build this, but I do want to think about why this argument's going to work. By saying we have a non-empty subset, by the way, S also is a subset of the natural numbers because every x is greater than 0. Since x in S satisfies x greater than 0, we know S is a subset of the natural numbers. By the way, I can't say, right, I had to say, maybe I should have said this earlier, but we couldn't say every non-empty subset of the integers has a smallest element. Right? Because you can have arbitrarily large negative numbers. So so it's really the fact that we have this bound on the left of 0 means that we get a smallest element. Okay, so we have a non-empty subset of the natural numbers. Thus, by well ordering, S has a smallest element. Let's just call it A. Okay, so this is sort of the formal how you would set this up, but I do want to talk about why this is true. Why is 1/2 not an integer? Maybe 1/2's an integer. You know? I said all the axioms for the rationals work for the integers except the well ordering principle. So the question, I want to somehow, just to give you an idea of how this proof's going to go without just sort of doing it and not motivating it at all. Let's see what would go wrong with the well ordering principle if 1/2 was an integer. Okay. We know from experience that 1 is the smallest integer. Smallest positive integer, smallest natural number. What if 1/2 was a natural? It would be a natural number because it's greater than 0. If 1/2 is a natural number, what else is a natural number? What else do you add to natural numbers besides 1/2? Every other fraction, like 1/3? 1.5, you could do 1/2 plus 1. You could definitely get a quarter, right? I don't know about a third, but you could definitely get, why is a quarter natural number if a half's natural number? What's that? Yeah, but we have closure, right? It's because of closure. So a quarter would be a natural number. What else would be a natural number? An 1/8, a 16th, a 32nd. Natural numbers are closed under multiplication. So yeah, kind of going with what you're saying, like we could get well, we could certainly make it smaller and smaller fraction, right? A 64th, a 1/28th, a 2/56th. Why does that feel wrong? Or what does it violate? You agree that it's sort of that violates the well ordering principle? Because now you would have a set of natural numbers with no smallest element because you keep multiplying by a half again. So that's it's kind of interesting. That's kind of like, it's so weird that this very vague, weird statement ends up being a good axiom, but you can kind of see it. If 1/2 was a natural number, then you could sort of make numbers arbitrarily small. And that means the natural numbers would not have a smallest element. Right? So yeah. So let's see if we can do this formally. So I guess the idea, if I just want to sort of like say an aside, is that if say 1/2 is in N, then so is a quarter, an 1/8, a 16th, 32nd, and so on. And and S really is what I want to say. And then S has no smallest element. But I got to do it a little more generically than this, because not just about a half, right? So that's kind of the idea. So A, let's see, we know A is greater than 0 and A is less than 1, right? I'll write that as two separate statements. And we know every other element of this set. Remember, this is a set of integers between 0 and 1. We know every other element is bigger. I guess the question is kind of emulating if A is in the role of 1/2, what do I want to show is also in S? 1/2 A. Well, it's kind of funny because if A is actually 1/2, like we don't know about what 1/2 is. I'm saying like turn 1/2 into A. Then if in your statement 1/2 equals A, then what are you really saying? Yeah, well, like, yeah, it's basically you're saying A squared, right? Like, so the claim is going to be that A squared is in this set, but that it's also smaller than A. And that's going to violate the fact that A is the smallest element. So just like if 1/2 was the smallest element of this set, then it wouldn't be because 1/4 is actually in the set. So very similarly, if A is in the set, then A squared is also going to be in the set. We have to show that. So let's consider A squared. The claim is that A squared is going to be in the set and less than A. So we need to show those, right? So let me just write this claim. A squared is in S and A squared is less than A. I guess claims. And then these two together would contradict the fact that A is the smallest element. Would contradict A being the smallest element. Of S. Does that make some sense? Like, and again, in your mind, the avatar is like A is like a half. Because we do agree that when you take powers of numbers less than 1, you should get smaller numbers, right? So let's see if we can actually prove both of these. So, well, I think we can actually. In fact, you had a homework problem that is very helpful for this. What's the homework problem that you had? So I actually said it here, A is greater than 0 and A is less than 1. We had something like if A is greater than 0 and B is less than C, then what? What was the conclusion? Right, we could basically multiply both sides of an inequality by a positive number and preserve the inequality. So A is greater than 0 and A is less than 1. Okay. Implies that A times A is less than 1 times A. Right, we're basically multiplying both sides of an inequality by a positive number. I feel like I should color code my A's here. This A is there is this A. This A is right. That's what we're saying, like using that statement, that fact we proved. You multiply both sides of A less than 1 by that. So A squared is less than A. And moreover, is A squared greater than 0? Where does A live? Oh, that's true, actually. Yeah, we could do the same thing with the A greater than 0 and A greater than 0. I was thinking that we know A is a natural number because it lives inside S, right? And therefore, and since natural numbers are closed under multiplication. But yeah, yours is, I like yours too. So, so that's bullet point 1, bullet point 2. Yeah, let's do yours. A is greater than 0 and A is greater than 0. Let me try doing this color coded. This is green A and yellow A. That's a Y. What did I just do? The word yellow. I said the word yellow, so I wrote Y. Implies A times A is greater than A times 0, right? Multiplying that first A by both sides of the second inequality. Being way over. Implies A squared is greater than 0. So, nope, that's wrong. Also, so I'm trying to show that A squared lives in S. So what do I need to show about A squared? Besides it being. So, right, although we said it's greater than 0, or we said A squared is greater than 0, so I think we just sort of proved it's a natural number. What else do we need to show to be in S? To live in S, what do we need to show? What are the conditions for living in S? Someone? If I want to say A squared lives in S, I have to show that inequality, right? So I need to show A squared is less than 1. Why is A squared less than 1? Anybody see it from stuff written on the board? Actually, do we ever prove this? A is less than B and B is less than C, then A is less than C. You see where I'm going with this? Also, A squared less than A and A less than 1 implies A squared less than 1. And these two together imply that A is an element of S, right? A squared, sorry. A squared is an element of S. Therefore, A squared is an S. Just because it satisfies both, it's between 0 and 1. So A squared is an S. Just to recap what I said here, we've shown A squared is in S, but A squared is less than A, the smallest element of S. I mean, I guess you could say that this actually shows A squared is not in S, right? And now you have a direct contradiction because you have A squared is in S and A squared is not in S. You could say it that way, or you could just sort of say like being smaller than the smallest element is a contradiction. Does that make sense? Maybe we'll say it that way. Implies A squared is not in S. And then these two together make a contradiction, clearly. So therefore, our assumption was that S was not empty. So in fact, S is empty. And there are no integers between 0 and 1. This is a strange proof, I think. I mean, I love it. I think it's a great proof, but it takes some time to wrap your head around. It's like, there's a lot of moving pieces, kind of. It's like, again, I think if you think of the 1/2 example, then it sort of makes sense what we're trying to do. In fact, I talked about this before, like someone like Fermat would have called this an infinite descent, right? You're getting smaller and smaller things. And so this is a way to avoid the infinite descent, is just to, you're basically, instead of creating a set that makes smaller and smaller elements, you just pick the smallest element and then prove it's actually not the smallest. Then you get a contradiction. Okay, questions about this? I love these well-ordered proofs, but they're an acquired taste, I think. Induction seems a little more straightforward. You know, but again, formulating this as an induction proof would be quite difficult. I'm not even sure how you would. You should be able to if they're equivalent, if well-ordered is equivalent to induction. But this is such a weird proof compared to the induction proofs we've done, right? Okay. Okay, good enough. So that's an example of a well-ordered proof. We're going to see some other ones. I'm still going to sort of like layer in some of this axiomatic number theory stuff because I do eventually want to build up to proving the unique prime factorization. But we do need some more stuff there. Okay. Let me just look at my notes for today and remind myself if there's anything else I wanted to say before we go on to this handout. No, I guess we did say. I used 243 instead of 7, but yes. So here's a handout. Let me open this and then share screen. So just for fun, I wanted to go ahead and introduce modular arithmetic because we're going to use it for lots of examples. Yeah, and this is something that is going to come up a lot. Like I said, it's for a lot of examples. It's just a good thing to know in math, modular arithmetic reasoning. So there's this notation. We use this x with these sort of 3 bars, y mod m, and say x is congruent to y mod m. There's other ways to say it, equal, equivalent, modulo. This definition looks a little strange at first. If there exists a case such that x equals y plus mk, like I said, it really means they differ by a multiple of k. And actually, if you think about it, like a mod 10 example is a good example. Like all these numbers are the same mod 10. It basically means it has the same units digit, right? Because if you think about it, the difference, if you take any of those two numbers and you take the difference, it's a multiple of 10, right? Another way you can say this is to say they have the same remainder when you divide by 10. It's another way people talk about mods, or well, same remainder when you divide by m. These all have remainder 3 when you divide by 10, right? And I did mention, like, you could also go into the negative numbers. So all of a sudden, I said they had the same units digit, but that's only if they're positive. If they're negative, you end up getting 7s instead of 3s. But do you sort of like believe what all this is saying? Like basically, any one of these, I could fit x in any, if I pick any two of these, I could fit this equation with m equals 10, right? Like 23 is 73 plus 10 times negative 5. You know, just 73 minus 50, right? Okay, you all look kind of stunned. I don't know. Does it make sense? It's a thing that's going to be like quite prevalent in math, like modular thinking. It's an interesting idea because, I mean, you've probably seen this before. Like, it's a useful idea because sometimes you just want to consider the units digit. Like to tell if something's a multiple of 5, you just have to look at the units digit and see if it's 5 or 0, right? Or another thing, oh, I didn't think about putting it on the handout, is have you ever looked at the pattern in the units digit of perfect squares? Let's do that for fun. I think this is on, hold on. This is on screen. Yeah, I think you can see the board over here. I just tried to write perfect squares, like, and look at the units digit. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 256. Why does my brain stop working? What is this? 16, 17, 17? Wait, this is 11, 12, 13. Wait, what did I skip? Yeah, that's the problems I skipped. Thank you. 225, 256. 289, 324, 361, 400. We keep going. 441, 484, 529, 576, 625, 676, so on. I'm just adding the next odd number each time. Remember we did that? No, not really. I just probably memorized these at this point. 841, 900. Do you see a pattern in the units digit? It's kind of a nice pattern, right? 14965 6941. It's actually palindromic, and it repeats every 10, right? So by the way, this shows you something. This shows you that a perfect square can never end in 2, 3, 7, or 8. So if I ask you the number that's 1,000,000 2s in a row, is that a perfect square? You can immediately say no. If I ask you the number that's 1,000,000 4s in a row is a perfect square, I don't know. But you can often give negative answers with modular thinking. Like now we know no perfect square. If you sort of believe this pattern continues, and we can talk about why, then you can say no perfect square ever ends in a 2 or a 3 or a 7 or an 8. And there's sort of reasons why this is true. The palindromic thing is also interesting, like why that's true. So anyway, so this is what modular arithmetic is. Maybe I was going to just have us do some group work, actually. I will say sometimes you're told to like reduce mod m, which means to like turn x in, like find the number that it's between 0 and m minus 1. So like mod 10, it would find the number that's equivalent to between 0 and 9. In other words, I should take the units digit. Like that would be like, if I took this number and said reduce mod 10, you could just say 3. It's 3 mod 10, because you just look at the last digit, right? And you can add or multiply. And so like, this is the thing, like if you say 3 plus 4 mod 5, 3 plus 4 is still 7, but 7 is really 2 mod 5 because you just take a 5 away. You can also think about like subtracting off m's. 4 times 5 is 20. Do you agree that that's 6 mod 7? 20, you take away a 7, you get 13, you take away another 7, you get 6. 4 minus 7 is -3, but I could add 11 to that to get 8. So there's ways to like do arithmetic. Basically, you could do arithmetic just with these numbers and always move things back into this arrange. So like I can do all this arithmetic where I just only use the numbers 0 through 4. Because every time I get out of the range, I can just move back into it. Does this make sense? Like I said here, that's mod 100. One way to think about like what 47 is mod 11 is just to think about like, well, if I divide by 11, 11 goes into 47 4 times with the remainder 3. That's 3 mod 11. And then also just the last, I'll let you guys do these problems, but the last one is even something like doing multiplications and stuff can be useful. Like if I just want to know what 12 times 13 is mod 10, there's no reason to actually multiply it out. Instead, you just say, well, 12 is 2 and 13 is 3. So 12 times 13 is 2 times 3 is 6. Like, right? You don't need to actually multiply out 12 times 13 to know that mod 10, 12 times 13 is 6. That makes sense. Or something like, I said also, sometimes it's more helpful to pick a number, like the smallest remainder, not necessarily positive, but like you could have a negative or a positive remainder. And so like mod 13, if you think about like 5 to the 4th, that's 25 times 25. If I reduce 25 to 12, right, by subtracting off 13, that's well and good, but that's still kind of a big number. But you can even reduce 12 to -1. And then you can just do -1 times -1 and get 1. So like there's just nice little computational tricks and stuff you can do. I don't know, I feel like you guys are just staring at me and I should probably just let you work in groups on this. Just practice yourselves. Yeah. So why don't you guys, let's go into groups for the last like 20 minutes or so. You can, like I said, just do number 1, just to like just to get used to sort of like what something is mod 7. You might skip number 2 for now and come back to it and do number 3, because that's kind of like using the same reasoning as we did here. You can compute all of these things pretty easily. And then you might go back to number 2 and try to prove it from the definition. And then number 4 is interesting. I think that's it for the page, just 1-page handout. Okay. So groups, can we do groups? Same groups as usual? Yeah? Ooh. Ibuprofen did the trick, kind of. My back feels, I took 2 today. Like, I took 1 yesterday, it didn't really help. Thank you, yeah, it's annoying. Yes, please, or, yeah. Sorry, 1 is almost off the screen.
That's funny. I had an opposite experience. I had like 5.
You might want to pull this up on a device or something. But yeah, do number 1 first. I heard 31 minus 7, that's good. Let's get what I'm asking. Yeah, definition's a little abstract, but mod 7 kind of means you can just like add and subtract 7s to the number and it's considered equivalent. So you could write down a bunch of numbers. Biggest negative is kind of awkward. I meant like closest to 0. Yeah. And you could keep increasing by 7 like they did. Percentage sign, is that like a computer science thing? Yeah. Okay, so I think everyone got the idea with number 1. It's just, you can just write down a bunch of numbers. But basically you say 31 is 3 mod 7. But maybe do number 3 and then come back to number 2. And if you might want to look at the idea is you're going to reduce before you compute. So like, what is 15 mod 7? Right. I think I must have done a bad job explaining this. So I guess what I'm trying to say is you can reduce the 15. You don't have to worry about taking the 100th power. You can actually reduce the 15 mod 7. What's 15 reduced to? Mod 7. It's 1. So this is the same thing as 1 to the 100th minus 1 mod 7, which is 0. So just shift by 7s. Like if you subtract 7s, 15 minus 7 is, and 8 minus 7 is, or if you divide 15 by 7, the remainder is 1.
So the number will always be less than the mod number.
When you reduce, yeah, that's right. Yeah, that basically right, that you can reduce before you take the power. So 15 just reduces to 1. Yeah, 50, yeah. Well, it's fine. It's still true. Still true. Yeah, but we can just think about moving by 7s. So there's nothing wrong with saying, and those are all true statements. Well, 7's not 1 mod 11. No. So here what I'm saying actually is do 7 times 7 first, and then reduce mod 11, and then times 7, like build up to the 5th power. Yeah, and then that's, what is 49 mod 11? If you reduce it, it's 5 more than 44, right? So 7 squared is 5. I really feel like I didn't do a good enough job explaining what I wanted people to do. So when you're going to calculate 7 to the 5th, instead of doing 7 to the 5th first and then reducing mod 11, multiply by 7, reduce, multiply by 7, reduce, multiply by 7, reduce. Like build up to 7 to the 5th, but each step reduce mod 11 first. It makes the computations easier. You know what I'm saying? So like first you look at 7 squared. What's 7 squared mod 11? Then you multiply that, whatever that is, you multiply by 7 again to get 7 cubed. Whatever that is, you multiply by 7 again to get 7 to the 4th. And you just keep reducing it every step, so you don't actually ever have to use large numbers. Does that make sense?
Oh, so you get negative 32 and 32.
Two left over times 7, 35. 3 left over times 7. Back to 10.
10, you got 10? I think that's probably right. I do think that's right. I think it's 10. Does that make sense?
So when we're doing mods, are we looking for one number? How would we write this out? Like,
I see. How would you write out?
7 to the 5th model of it if the answer is just 10.
Yeah. Yeah, you just say 7 to the 5th is congruent to 10 mod 11. Yeah. But right, you'd have to write out the computation somehow, like. Yeah, so 7 squared is 5. So 7 cubed is 7 squared times 7, right?
Oh, so it'd be 30.
Yeah, it's like,
Oh, I see.
oh, that's really funny that I didn't change the 2013 to 2022. Clearly, I found that from some handout a long time ago and just copied it. It's embarrassing. So for this one, you probably want to just do powers of 3 and compute the mod 11 until you get back to 1. Oh, is that what you did? Well, that's interesting, right? So like, yeah, if you find it, I guess I'm claiming that there's going to be a pattern that repeats. So compute power, for the last one, compute powers of 3, but reduce mod 11 each time and look for a pattern. I claim that there's sort of a pattern. Did you guys get the 7 to the 5th one? Did that make sense? What did you get? You got 9? Other groups got 10. Did you guys get 7 to the 5th? Okay, yeah, I don't know. I think I'm being confusing. So do you agree that 7 cubed is the same thing as 35? Mod 11? That it's like 7 squared. 7 cubed is 7 squared times 7.
Yeah.
Which is congruent to 5 times 7, which is 35 mod 11. And then what's 35 reduced to? Mod 11. What's the nearest multiple of 11? 33. So what's the remainder? 2. This is 2 more than 33. So now you just showed 7 cubed is 2 mod 11. And so you can do the same thing with 7 to the 4th, right? You can sort of continue. Does that make sense? Oh, 2 times 7, yeah. Yes. Ever pause the recording? I just want to pause the recording. Hold on. Sorry, just want to pause the recording. Yeah. Oh, and the computer says we actually have more time left. But you can think of you can basically take reduce mod 11, like reducing mod 11 or mod anything. It really just means, in my mind, it means take the number and divide by 11, take the remainder when you divide by 11. Right, so if I take something like, what were some of the numbers that popped up, like 49, right? 49, when you divide by 11, you get, what's the quotient when you divide by 11? 4, it goes in 4 times, right? And the remainder is 5. So this is 44 plus 5. And honestly, when you see multiples of 11, you can almost just replace those by 0. Because multiples, when you divide, if you take the remainder when you divide by 11, anything that's a multiple of 11 will be 0. So another way to think about mods is like, anytime you see an 11, you just make it go away, make it 0. So that's 5 mod 11, right? And so this powers, for example, this powers of 3. Let me just do like n and 3 to the n mod 11, maybe like a table. So 3 to the first power is 3, 3 to the second power is 9. But 9, when you reduce mod 11, you divide by 11, you still get remainder 9, right? So when you multiply that by 3, you get 27, but you could reduce that mod 11 now. What does that reduce to, mod 11? What's the remainder of 27 when you divide by 11? 5, 5, 5. So that's really 5. And then when you multiply by 3 again, so that's 3 to the 4th, you get 5 times 3, which is 15, which really reduces to, what's 15 reduced to? Everyone, is everyone on the same page here? If I divide by 11 and take the remainder? Everybody shout it out. 4, okay. I'm trying to figure out where I confused you. That must not be that, okay. And then when you multiply by 3 again, you get 12, and that's your 1. So you get 3 to the 5th is 1. You could keep going though. I could do 6, that's 1 times 3 is 3. 7, 3 times 3 is 9. 8, 3 times 9 is 27, which we already saw was 5. So you get this sort of pattern, this repeating pattern in the powers of 3 mod 11. Does that make sense? I will say computationally, sometimes it's nice to replace a slightly large number with a smaller number closer to 0. Like this is actually equivalent to -2 because I just add or subtract 11. Right, if you add or subtract 11s, if you're saying I'm taking in the remainder when you divide by 11, when you add or subtract 11s, you're not changing that remainder. And so you could do -2 here, and then this would become -6, which you could then replace by 5 if you wanted to. You know, so you can do these things sometimes where you use small negative numbers, like I did in that example where I took the 25s, like I computed 5 to the 4 in kind of a fast way, mod 13, by saying, well, think of this as 25 times 25. The reason I did that is because 25 is close to 26. And 26 is a multiple of 13, right? So I sort of thought about it. I was like, oh, 25 is just actually -1. Because you could think of the remainder being -1 when you divide by 13. You can think of it being 12, or you can think of it being -1. You can either take the positive remainder or you can take the smallest remainder. I didn't really specify this. In some cases, it's going to take the positive remainder. Some cases, you might just want to take the smallest remainder. And you can have a smaller remainder sometimes if you allow a negative remainder. So 25 divided by 13, you might prefer to make, instead of quotient 1, remainder 12, you might prefer quotient 2, remainder -1. And then we don't care about the quotient, we just throw it away, we just take the remainders. So there's just, you got to get used to this, and I'll give you, well, I won't put it on the test because we haven't done, but for the following week, I'll definitely give you a lot of practice. And we'll do stuff with mods throughout the semester. I just wanted to like introduce them to you today. And some of you had seen them in computer science, clearly, because I saw the percentage sign, which is like a computer science notation for mod. But it's an important concept. Like I was saying, mod 10 is just the units digit. Some people introduce mod 12 by like clock arithmetic. Like if it's 10 a.m. and I go 6 hours ahead, it's not 16, well, it's 1600 hours, I guess, but it's 4 p.m. So you've gotten past 12 and reduced, right? You get to 16 and then you divide by 12, take the remainder, or just subtract off of 12, you get 4. Mod 2 is like parity. Numbers mod 2 are either 0 or 1. So even numbers are 0 mod 2 and odd numbers are 1 mod 2. So there's just all sorts of ways this stuff comes up. So, okay, I'll stop there. Sorry for butchering that a little bit, but hopefully you guys are kind of used to it now, and then I'll give you some practice. But okay, we are done. Thank you. Sorry again for being